Okay, we need now to span three functions, right? Which are 1 over 1 minus x, 1 over 1 minus x squared, and 1 over 1 minus x cubed, right? For this function for k1, 2, and 3. There are two ways, at least, in which we can do this, right? And I'm going to show you both. So the first one is, well, we focus on this one, right? So f is equal to 1 minus x to minus k. And this is the binomial series, remember? The binomial series has this form, and the expansion goes like this. Alpha over n, x to the n. Alpha is any real number, and alpha over n is equal to this divided by n factorial. Okay, that's the definition of this series. Well, not the definition, that is the Taylor series for this function, right? The radius of convergence, by the way, is this, okay? Right. So in this case, what we have is first, instead of x plus x, we have minus x. So we have to introduce here minus x, right? And the second thing that we have is that alpha is negative k. So what we have here is therefore this series is negative k over n, right, minus x to the power n. So formally, this is the series, right? So let me just, let me first transform this number into something more easy to recognize. Okay, so we have minus k over n. And according to this formula, this is equal to minus k times minus k minus 1, minus k minus 2, etc., up to minus k minus n plus 1 divided by n factorial. All right, there are n factors here, okay? There are n factors here, right? This goes from alpha minus 0 to alpha minus n minus 1, so there are n factors, right? And all of them are negative. So we can take out the negative number as minus 1 to the n, so one negative factor per each of these factors, right? So we have minus 1 to the n, and then we rewrite the factors as positives. So we have k plus 1, okay, k plus 2, etc., and the last one is k plus n minus 1. And down here I have n factorial. All right? Okay. Now, so this is the expression that we have here. And if we want to put it here, remember that you have here minus x to the n, and minus x to the n is minus 1 to the n times x to the n. So this is equal to the sum from 0 to infinity of this number, which is k plus 1, etc., k plus n minus 1, right, divided by n factorial, okay? And then minus 1 to the n from here, another minus 1 to the n from here, and then x to the n. So this is minus 1 to the n squared, which is equal to 1, right? So we can just cancel that. And then we have the expansion of 1 minus x to minus k for arbitrary k, which is equal to that, right? It's equal to the sum from 0 to infinity, k plus 1, k plus n minus 1 over n factorial, x to the n. There's a much nicer way to write this, and it's the following, right? You can multiply by k minus 1 factorial in the numerator and the denominator. If you do this, in the numerator you have this, right? And in the denominator, what you have is n factorial k minus 1 factorial, right? And look at this. What you have here, up here, is the product of all the factors starting from this and decreasing one by one up to 1, right? Because you have k plus 1, k minus 1, k minus 2, etc., right? So in the numerator, what you have is this number, factorial. And in the denominator, what you have is k minus 1 factorial, n factorial. Well, it turns out that this is a combinatorial number. This is the combinatorial number, a real combinatorial number, because these are integers. It's this combinatorial number. All right? The sum of these two numbers is equal to this. So therefore, this is this combinatorial number. So if you remember this, you can also write this as this form, where these are true combinatorial numbers. Okay? It's to the end. Well, it doesn't matter, it doesn't change the fact that this is an infinite series, right? But anyway, it might be easier to calculate these combinatorial numbers. But in any case, the factor we're calculating, the coefficient, is this one, right? In the simplest form of this coefficient is this one. All right. So now we have k1, 2, and 3. So let's try to see what this combinatorial number is in these cases. So for k equal to 1, what you have is 1 minus 1 is 0. So this combinatorial number is equal to n over n, which is just 1. And the series you obtain is the sum of x to the n, because the coefficients are all equal to 1. This is something that we already knew, because this is the geometric series, right? So it's an alternative way of getting a sum that we already know. And of course, the radius of convergence is 1, right? Because that is the radius of convergence of this series in general, okay? This series here in general. All right. So we have this for k equal to 1. For k equal to 2, 2 minus 1 is 1, so we have n plus 1 over n. And this number is just n plus 1. So what we have is the series of from n0 to infinity of n plus 1 x to the n, and that is 1 over 1 minus x squared. You might remember that, well, this is the sum of two series. Well, this is the result, right, that we have obtained. This function has this Taylor series. But you might remember that this series here is what we call, at the beginning of series, the arithmetic geometric. Arithmetic geometric. Okay? And this series here is the sum of this plus this one. Right? Because it's n plus 1, what we have here. This one here is 1 over 1 minus x. So the arithmetic geometric is equal to 1 over 1 minus x squared minus 1 over 1 minus x. If you multiply numerator and denominator by 1 minus x, what you get is 1 minus 1 minus x over 1 minus x squared, which is x over 1 minus x squared. If you remember, that is the sum of the arithmetic geometric, which we obtained at that time in a more painful way. Okay, this is a very simple way of getting that out of the Taylor expansion of this function here, right? Okay, now let's see what we obtain for k equal to 3. For k equal to 3, we go here, we have 3 minus 1 is 2, so we have n plus 2 over n, and that is n plus 2, n plus 1 over 2, okay? So what we have is that 1 over 1 minus x cubed has this expansion, the sum from 0 to infinity of n plus 2, n plus 1 divided by 2 x to the n, right? Fine. That's the answer to the problem, but again, let me transform this a little bit, right? We have n plus 2 times n plus 1, and that is n squared plus 3n plus 2, okay? We multiply these two here, so what we have is that 2 over 1 minus x cubed is equal to the sum from 0 to infinity of n squared x to the n plus 3 the sum n x to the n plus 2 the sum x to the n, right? And this is the arithmetic geometric, whose sum is this, as we've seen before. And this one here is the geometric series, whose sum is equal to this. So from this expression, we can obtain this other sum. The sum of this is equal to 2 over 1 minus x cubed minus 3x over 1 minus x squared minus 2 over 1 minus x. So if you want to know the value, you can expand this, simplify, and then you have your answer for this. And clearly, we can continue this procedure and obtain the series for any power that we have here. Actually, if we take k equal to 4, in that formula we will get n plus 3 over n, which is n plus 3, n plus 2, n plus 1. And down here we have 6, 3 factorial, right? Okay, so that means that 1 over 1 minus x to the 4 is equal to the sum from 0 to infinity of n plus 3, n plus 2, n plus 1 over 6, x to the n. And if you expand this, there will be a term that is n cubed, right? So we can calculate the sum of n cubed times x to the n out of this formula, right? And the previous ones. So this is a valid procedure to obtain any series, the sum of any series of this form, and the sum from n0 to infinity, n to p, x to n. It can be tedious because if p is large, you have to repeat this many times, but at least there is a procedure to calculate this. Okay, this is the first way to solve this problem. And as I said, there is a second one, right? In which the only thing you need to know is this, which is something that we already know since we talk about series for the first time, right? This is the geometric series, is convergent in this region, right? And the sum is 1 over 1 minus x, okay? All right, let's take the derivative of this, okay? We take the derivative of this, what we have is 1 over 1 minus x squared. And in power series, the derivative can be just taken 10 by 10. So what we have is this. We sum from 1 because for n equal to 0, this is a constant, and the derivative of a constant is 0, right? And we get n x to n minus 1. Well, in any case, if you keep n equal to 0 here, as you have an n here, for n equal to 0, there's no contribution of this term, right? So you can start at 1. And now you can shift the indices, right? You can increase the index by 1 here and decrease it by 1 here, and then you have the sum from 0 to infinity, n plus 1 x to the n. The radius of convergence is the same as the radius of convergence of the derivative is the same as the radius of convergence of the function. You see, this is for k equal to 1, and this is the function for k equal to 2. So we obtained the same expansion that we have obtained before with a different method, just taking a derivative of this one. And we can continue. We can take the derivative of this, and the derivative of this series is 2 over 1 minus x cubed. And if you take a further derivative of this function here, this expansion here, we have the sum. Again, n equal to 0 is a constant, so we begin at 1. And then we have n plus 1 times n times x n minus 1. And shifting the indices, we have n plus 2, n plus 1, x to the n. Again, the radius of convergence is 1 because that is the radius of convergence of the previous series. Now divide this by 2, and then you get the result for k equal to 3. 1 over x minus x to 3 is equal to the sum from 0 to infinity, n plus 2, n plus 1 over 2, x to the n. Exactly the same result that we have obtained before. And obviously you can continue with this procedure over and over, taking the further derivatives, and you will get the case k equal to 4, the case k equal to 5, 6, 7, etc. right? By taking derivatives one by one. So these are two alternative procedures to get the same result here. In this particular case, because this is the binomial series, right? We have a formula for an arbitrary value of alpha here. But anyway, if we didn't, just taking derivatives, we obtain sequentially these different functions for which we want to calculate the expansion. So once we know one of them, we can obtain the others by differentiating the expression. Okay?